So in this tutorial we are going to work with logic gates, and logic gates are basically digital logic circuits. And as you can see here, I have written some of the logic gates here which we are going to discuss in this tutorial. So basically these logic gates perform very small operations, and when these logic gates are combined they will just form combinational circuits. So logic gates is the basic building block of the circuits that our computer operates on. So why they are known as digital logic circuits? Because they operate on digital signals, and digital signals are basically 0 and 1. And we know that our computer works on the binary signals 0 and 1. These are the electrical circuits, and basically since they perform some logical operations, they are known as digital logic circuits. So let's move on to the logic gates that we are going to use in this example, and we will also see how these perform various operations. So let's study with the first one, which is the AND. First one is the AND logic gate, and the representation of the logic gates is like this. A and B are the input signals. So basically we give two input signals to the AND logic gate. This is basically the representation of the AND logic gate, and when these two signals passes through this AND logic gate, it will form it will give some output or result which is known as X. So basically AND is used to it is algebraically you can write X is equals to A dot B. So we are going to make use of truth table, and we will just write some sample inputs, and we will see how these inputs when passed in these logic gates, what will be their output. So let's study the first one, which is the AND gate. So in the AND gate you can see the representation here. So if the input is 0 and B is also 0, then the output will also be 0. So when it just basically works like the AND operator in maths, which just says that if two inputs are 0, then they are 0. If any one of the input is 0, then again the output will be 0. But if both the inputs are 1, then the output will be 1. So the idea is very simple. If all the signals that passes through the AND gate are 1, that means that the output will also be 1. But if any one of the inputs if any one of the input signals or both of them are 0, then the output will be 0. So this is basically AND gate. The next one is the OR gate. The representation of OR gate is like this. It is the curved line, then it has a structure like this. Again we will pass two inputs to this OR gate, and it will give us an output. In case of OR gate, it is represented algebraically as X equals to A plus B. So in case of OR gate, what we are going to do is the outputs are going to change. So in case of OR gate, if any one of the inputs or if any one of the input signals are 1, then the output will be 1. So if any one of the signal is 1, then the output will also be equal to 1, as you can see in this example. So if both the input signals are 0, the value will be equal to 0. So that's how these gates are basically circuits. So whenever you will pass some inputs to these gates or these circuits, they will give you an output. And the combination of these gates are used to perform some very heavy operations in our computer system. So let's study the next gate, which is the NOT gate. And this NOT gate is basically used to invert the signal given to it. So if the given signal is 0, then the output will be the inverse of it, which is 1. Basically, 0 represents the off state and 1 represents the on state. So if the signal is there, it will be marked as 1, and if there is no signal, it is marked as 0. So if you will give 0, or if there is no signal that passes through the NOT gate, it will automatically convert it to 1. And if the signal, the input signal is 1, then the output will be 0. Like this. So NOT gate is also very simple, and this is the and the OR gates. Then comes the and, which is not AND gate and not OR gates. Both these gates are basically and OR gates, but you can see a little circle over here which represents that it is a NOT operation or the invert signal operation. So in this case, what we are going to do is we are going to just invert the signals that the AND gate will perform. So let's first check what will be the output if in case of the NAND signals. So in AND signal, we know that if both the inputs are 0, the output will also be 0. But since this is not AND, we are going to do the inverse of it. So we will make it 1. Similarly, in AND gate, if any one of the signal is 0, we will make it 0. But since this is the invert, which is the NAND gate, we are going to invert the signals and make it 1. 1 and 1 in case of AND gate will give 1, but inverse of it will be 0. So this is basically when you will give an input signal A and B like this, it is going to give you an output which is the inverse of the AND gate. The next one is the NOT OR gate, and NOT OR gate is basically, it is used to just invert the signals of the OR gate, as it is same as the NAND gate. So in case of NOT, we know that if there will be an OR operation, if any one of the signal is 1, the output will be 1. But since this is an OR gate, we are going to make it 0. And since both the signals are 0, the OR operation will get 0, but we will write 1 here. And similarly here also. So these are the 5 gates that we have done. Out of these two are known as universal gates. NAND and NOR are known as the universal gates. And the reason behind this is that you can use these two gates or the combination of these two gates to actually get these gates, which is the AND gates and the OR and the NOT gates. So let's move on to the exclusive OR and the exclusive NOR gates. As you can see here, I've written the symbol. The symbol represents nothing, but this is conventionally accepted. So whenever we will write a whole circuit, we will just represent these with the symbols. So in case of exclusive OR, the algebra looks like this. So we are going to use A and addition in a circle and B. So this algebra basically represents X equals to A complement B plus A B complement. In case of exclusive NOR, it will be A complement B complement plus AB. So let's study the truth table of the exclusive OR gate. In case of exclusive OR gate, we can see this whole algebra here, and this algebra says that A complement B plus A B complement. Initially the values of A and B are 0 and 0. So 0 complement is 1, 0 complement is 1, and B is 0. So this will evaluate to be 0. 0 plus A B complement. A is 0, so this will be 0. So 0 plus 0 will evaluate to be 0. So let's study what will happen in this case. In this case, the value of A which is the first input signal, is 0. So 0 complement is 1. 1 into 1 is 1. So here it will be 1. And it doesn't matter if it is 0 or 1 because this is an OR. You can see that this is an OR gate. So the answer will be 1. So let's talk about this one. So if the first one is 1, you can see that A complement will be 0 and B is 0, so this will be 0 plus AB complement. So A is 1 and B complement is also 1. So AB complement will evaluate to be 1. So 0 plus 1 will be 1. In this case, A complement is 0, so this will be 0, and B complement is 0, so both of them are 0, which will give us 0. So this is the exclusive OR gate. In case of exclusive NOR gate, the algebra is this. But simply what we can do is just invert the output signals of the OR, because that's what the NOT gate does. So what we are going to do is in case of exclusive NOR, we are going to invert the signals and we are going to write it like this. So these are the logic gates that we have studied. In the next tutorial, we are going to study combinational circuits, which are basically used to combine these logic gates and perform some more operations, some more complicated operations. So we will see that in the next tutorial.